Okay, welcome to Lecture 39. This is Chapter 9, Section 4. We're going to be talking about effusion and diffusion. But first, let's talk about random walks. Okay. Imagine you have a one-dimensional universe. Okay, and here we have a number line going out to infinity in either direction. And here at the origin, the 0 point, you have a bar. Now, at last call, the bar releases an infinite number of drunks. Okay? So the entire population of drunks, an infinite number of drunks is right there at point 0 in this one-dimensional universe. Now, every second, our drunks, are going to take a step, okay? And then they're going to fall down, and they're going to get up, and they're going to take a step. But every time they fell down, they forget where they were and which way they were going, so they're going to take a step in a random direction. Okay, so first time they're going to end up half of them over here, half of them over here. But then so at -1 and +1. But then the next time, half of these guys will head back to 0, half of them will head over to -2. Half of these guys will head back to 0, half of these guys will head out to +2. Okay. Now, over time, your drunks are going to spread out to cover, the entire one-dimensional universe. Okay. So imagine, there's an invisible line at some point on the curve, or on the number line, at the very edge of your crowd of drunks. Okay. So you have some number of drunks there on one side of the line, and over here there's no drunks. Okay. The next time they fall down and get up, half of them will cross over the line and half of them will move back in the other direction. Now, there are no drunks to go back over the line. That can't happen to the left, but you're always going to have some drunks moving to the right. And the same thing would happen if you had an invisible line over on the left-hand side of your infinite number of drunks. Okay? So that means that tick, 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 every time they fall down, they get up, the crowd is always going to spread out. Okay? And with every tick, every tick of the clock, they're going to keep on going further and further. And there's always going to be some back toward the middle. Okay, they're never going to disappear from any spot. So you get a distribution curve that looks, it starts out like this, an infinitely thin, infinitely sharp spike right there in the middle. Then they start to spread out, getting more and more diffuse, until eventually you just get a perfectly flat line across the entire universe. Okay. Sort of the opposite of the infinitely sharp, infinitely tall spike. It's the infinitely flat, infinitely wide spike. Okay. So that's a one-dimensional example of a random walk. Where these unthinking objects, and in the case of the hypothetical example, these drunks, are exploring the entire universe slowly, pointlessly, randomly over a very long period of time. Okay. And you can talk about that for gas molecules as well, only they're doing it in 3 dimensions. Okay, so you have your particles of gas existing in a 3-dimensional space. And they are constantly running around, running into one another, bouncing off one another, and thus they explore the space that they're in. Okay? So the gas particles will also go on that random walk. Okay? So imagine, you have a room, full of gas. It's not a vacuum. Okay? And you have a box, or maybe just you can call it a balloon, what have you, full of other gas. Okay, so let's call this air outside, and then some gas inside your box. Then you open your box, the gas is going to escape. Now, because it's not a vacuum inside your room, okay, the gas inside the box won't just expand to fill the room because there's already air there. Instead, what's going to happen is it's going to diffuse out into the room. Okay. It's going to go on a random walk, and it's going to slowly make its way throughout the space inside that room. That's what diffusion is when a gas slowly explores and fills a space. It will slowly mix with a gas that's already present. So technically, diffusion is gas spreading through space along a concentration gradient. So wherever the gas is higher in concentration, it will move from there to wherever it's lower in concentration. Okay. Once again, imagine our invisible line. Okay, let's say there's 12 particles of your gas on this side, and there's only 4 over here on this side at time t, right? Well, half of them will go in either direction. So let's go ahead and say these will go in that direction, and these will go over there. These will go in that direction. These will go over there. Okay. So more invisible lines. Such that now we've got 6, 2, 6, and 2. And next time, you'll end up with 3 going in this direction, 1 going there, 1 and 3, 3 and 1. And now we have, at time t equals what have you, 1, 4, 4, 1, 3, and 3. Okay, so basically, this is just confirming what we already saw. When you have any sort of concentration gradient, those drunks are going to be spreading out. Okay, so they'll just go from where they are to where they aren't, where there's more of them to where there's less of them. Okay. So that's why things will always mix in that way. When they're free to move, they'll end up sort of uniformly spread out, okay, so that they'll be everywhere and equally concentrated. It's sort of like nature abhors a vacuum. Everything will diffuse in that way until they're nicely mixed. And while they're diffusing, each particle of gas will be free to move along its mean free path. That's just a concept that says, average distance between collisions. Okay. Remember, the particles of the gas are flying around randomly, running into one another. And the mean free path is just how far they fly in between collisions, how long they get to move before they run, but from one collision to the next. So the more particles of the gas there are, the shorter the mean free path is. You can think of it as the distance of the step the drunk gets to take. And the longer the step, the further the mean free path, the faster diffusion is going to happen. Just because, the further you can move, the faster you can move. And another thing that affects diffusion is the concentration gradient. So the higher the concentration gradient, the faster diffusion is going to happen. Just because, think about it, at the beginning, it's each step the drunks take is very dramatic because there's a huge population of drunks there moving out. Toward the end, there's far less of that sort of behavior just because the difference between any 2 points on the number line is less pronounced. So instead of being an infinite number of drunks versus 0 drunks on either side of the line, it might be 1,000,001 versus 1,000,000. Okay. So a slight difference, but not a huge difference. So, talking about diffusion, It doesn't always have to be in an empty room. You can think of diffusion as happening along a pipe as well. So it's diffusing along this pipe. The factors that affect diffusion speed are pressure, area, and gradient. So the higher the pressure, the slower the diffusion. Just because higher pressure means more particles, means more collisions, we're talking about a shorter mean free path, so it's going to slow down the rate of diffusion. And obviously the highest rate of diffusion would be a vacuum. Okay, when it's expanding into a vacuum, then there's no particles there to stop the advance. And the higher the pressure, the more gas there already is there. Surface area means bigger area is faster. Oops, not fast, but fast diffusion. Okay. Just because, think about it in terms of the line. Small area means, a small possibility of a gradient. A large area means a greater possibility for your gradient to act over. More space for it to explore, in other words. And finally, your concentration gradient. High gradient equals fast diffusion. Okay. And that's just, again, more particles on one side of the line, fewer particles on the other side of the line. Okay. The other thing we can talk about is effusion. Effusion. So effusion. Effusion is related to, but distinct from, diffusion. Instead of freely entering a new space, effusion means you have a gas that's going through a small hole, okay, or pore. Okay. So that is effusion. But it's governed by very similar sorts of behavior. The gas has to be able to find the hole and move through the hole in that way. The reason you would think about this is because it's a very controlled form of diffusion, and it's easier to come up with mathematical laws for effusion, but then those laws can often be generalized to other scenarios. And one of the laws that we care about here is that the rate of effusion, if you're comparing two different gases, is related to the molar masses of those gases. Okay. So notice, you have A on top on the left, B on top on the right. Okay. So what this is telling us, first, is that a heavier gas will effuse slower. And it goes as the square root of the masses. The reason for that we'll get into later. But for now, just know that 4 times more massive means twice as fast, the rate of effusion. So, for example, if you have a balloon filled with O2 versus a balloon filled with hydrogen, the oxygen is going to effuse out of that balloon slower than the hydrogen. Latex balloons, they're not, perfectly solid. There's no such thing as a perfect solid. The gas can escape. That's why balloons shrink and so on. Let's go ahead and call it a helium balloon, not hydrogen. All right. So, hydrogen works. Okay. So, what are the relative rates of effusion? Well, you have rates H2 versus the rate of O2. Is going to be related to their molar masses. And the molar mass of oxygen, remember, it is a diatomic element, is 32 grams per mole, versus hydrogen is 2 grams per mole. So we're talking about the square root of 16, or 4, roughly speaking. So hydrogen is going to effuse 4 times faster than oxygen, because oxygen is 16 times heavier. So that is a general sort of rule of thumb. Okay? The heavier something is, the slower it will explore space, just because, it's moving slower. So diffusion and effusion both tend to follow this kind of rule. Just that the heavier something is, the slower it's going to move. All right, so that is a math light section. It's more concept heavy, focusing on diffusion and effusion. But you should remember that formula. Rate A over rate B is equal to the square root of MB over MA. Okay. So definitely remember that guy. That is an important and useful sort of formula. And that will do it for 9.4. I'll see you in the next lecture.